Hey, I want to tell you about the two strangest, most beautiful ideas a human being ever had. They're called the special theory of relativity and the general theory of relativity. A scientist named Albert Einstein figured them out over 100 years ago. And here's my promise: by the end of this video, you will actually understand them. Not pretend understand, really understand. Let's start with a race. Imagine you're riding your bike at night and you turn on your headlight. A beam of light shoots out ahead of you. Now, pedal faster. Pedal as fast as you can. Here's the question: can you ever catch up to your own light? The answer is no. And not just no because your legs get tired. Even if you traded your bike for the fastest rocket ever built, the light would still pull away from you at the exact same speed. Always. That one weird fact is a loose thread. And when Einstein pulled on it, the whole universe unraveled into something new. This video is in two parts. Part 1 is special relativity: what happens to time and space when things move really, really fast. Part 2 is general relativity: what gravity actually is. And I'll warn you now, it is not a pull. Ready? Let's go. Everything in special relativity comes from just two rules. Rule 1 is old. Galileo knew it 400 years ago. If you're moving perfectly smoothly, no bumps, no turns, no speeding up, there is no experiment you can do that tells you you're moving. Toss a ball on a smooth train and it goes straight up and comes straight down, exactly like at home. Close the shades on that train, and you honestly cannot tell if you're gliding along at 200 miles an hour or parked at the station. Physics works the same for everyone who is coasting. That's rule 1. Scientists say all motion is relative. That's actually where the name relativity comes from. Rule 2 is the weird one. Light always travels through empty space at the same speed, about 186,000 miles every second, fast enough to lap the whole Earth about 7 times in a single second. But here's the strange part: everyone measures that same speed. Fly toward a star, its light passes you at exactly that speed. Fly away, same speed. Light doesn't care what you're doing. That should bother you. If you throw a baseball forward from a moving walkway, the ball's speed adds up. Walkway speed plus throwing speed. But if you shine a flashlight from that walkway, the light does not go extra fast. It goes light speed. Speeds are supposed to add. For light, they don't. So Einstein, who is 26 years old and working a boring day job in a patent office, asked the question that changed everything. If the speed of light refuses to change, then something else must be changing instead. And speed is just distance divided by time. So if speed can't budge, maybe distance and time can. Now for my favorite idea in all of physics. Imagine the world's simplest clock. Two mirrors, one above the other, with a tiny blob of light bouncing between them. Every bounce is one tick. Light's speed never changes, and the mirrors never move apart, so this clock keeps perfect time. Tick, tick, tick. Now put that clock on a skateboard and roll it past me. I stand still and watch the light inside. From where I'm standing, the light isn't bouncing straight up and down anymore. Between every bounce, the whole clock slides sideways, so the light has to travel on a slanted path, a diagonal, and a diagonal is longer than straight up and down. Hold on to this, because this is the whole trick. The light in the rolling clock has a longer path to travel, but Rule 2 says light can never speed up to make up the difference. Longer path, same speed. That can only mean one thing: each tick takes more time. The moving clock ticks slower. Not because it's broken, because time itself is running slower for it. And it's not just like clocks. A wristwatch on that skateboard slows by exactly the same amount. So does a heartbeat, so does the aging of your body. They have to, remember rule 1. If clocks on a smooth ride acted weird, you could tell you were moving without looking outside. Time itself, everything that ticks, runs slower when it moves past you. Now, two honest warnings. First, the person rolling with the clock notices nothing. To her, her clock ticks normally, her heart beats normally, and it's my clock that looks slow, because from her point of view, I'm the one moving. Weirdly, we're both right. And second, at everyday speeds, this effect is unbelievably tiny. You will never notice it on a school bus. It only gets big near the speed of light. So, how do we know it's real? Nature runs this experiment on us every single day. Tiny particles called muons are born high above your head when invisible specks from deep space, flying at almost the speed of light, come crashing into the air. Muons live for about 2 millionths of a second, so short that almost none of them should survive the trip down. But they do reach the ground. Detectors catch them constantly. They make it because they're moving so fast that their inner clocks run slow. From our view, they age in slow motion. This leads to the most famous puzzle in physics. Take twins. One stays home, one rides a superfast rocket to a nearby star and comes back. When they hug again, the traveler is genuinely younger than her brother. Less time actually passed for her. So, why isn't it equal both ways? Here's the honest answer: only one of them had to slam on the brakes and turn around. Her ride wasn't smooth the whole way. That turn breaks the tie. And this isn't science fiction. Real atomic clocks have been flown around the world on ordinary airliners, and they came back a few hundred billionths of a second off from the clocks that stayed home. Exactly the amount Einstein predicted, once you add up both the speed and the height. Ready for the strangest one? A long train. Lightning strikes both ends at the very same moment. A girl stands on the platform, exactly halfway between the two strikes. The two flashes reach her eyes together. Same distance, same light speed, arrive together. So she says, those two strikes happened at the same time. Fair enough. Now ride along inside. A boy sits in the exact middle car. Remember rule one. As far as he can tell, he isn't moving at all. It's the platform that's rushing past him. So for him, the front of the train and the back of the train are exactly the same distance away, and light from each end takes exactly the same time to reach him. But the front flash hits his eyes first. Same distance, same speed, and one still got there first. There's only one way that works. For him, the front strike really did happen first. And here's the mind bender: he's not wrong. She's not wrong. They agree on everything they saw. They disagree about when it happened. Think about what that means. Whether two faraway things happen at the same time is not an absolute fact of the universe. It depends on how you're moving. There is no single master clock ticking above the universe that everyone agrees on. Your now and my now can genuinely differ. Einstein called giving up universal time the hardest step of all. Once he took it, everything else clicked into place within weeks. Time bends and space bends with it. To someone standing still, a spaceship zooming past doesn't just have a slow clock. It's also measured to be shorter, squished only along the direction it's flying. The pilot notices nothing inside her ship. Instead, to her, it's the distance to her destination that shrinks. Remember those muons? From their point of view, their clocks are fine, but the thick blanket of air above the Earth is squished thin, so the trip is short enough to survive. Two totally different stories, same ending, both true. Out of all this, Einstein squeezed one more surprise: the most famous equation in the world: E equals mc squared. Here's what it actually says in kid language: energy and mass are the same stuff in two different costumes. Mass is basically frozen energy, and the c squared is the exchange rate, the speed of light times itself, which is a stupendously huge number. Meaning, a tiny pinch of mass equals an absolutely enormous amount of energy. You already know a machine that runs on this equation: the sun. Every second, deep in its core, the sun converts about 4 million tons of its own mass into pure light and heat. That sunshine warming your face is literally the sun trading away little bits of its mass at Einstein's exchange rate and sending them to you as light. Once that light leaves the sun's surface, your face is only 8 minutes away. So that's special relativity. Two simple rules taken seriously. Moving clocks run slow. Moving things measure short. Now is not the same for everyone, and mass is frozen energy. Einstein published all of it in 1905, but something nagged at him. Remember Rule 1? It only covers things coasting smoothly in a straight line at a steady speed, and nothing that falls does that. Gravity got left out of his beautiful new picture. Fixing that took him 10 more years and one thought he called the happiest of his life. Part 2. Gravity. One day in 1907, Einstein was staring out his office window when a thought hit him so hard he later called it the happiest thought of his life. Here it is. A person falling freely does not feel their own weight. Think about the top of a big drop on a roller coaster, that floaty feeling in your stomach. While you're falling, gravity seems to switch off. Your keys, your backpack, everything falls right alongside you, floating. Einstein turned that feeling into an experiment. Picture a windowless elevator. In version 1, it's falling freely toward Earth. In version 2, it's floating in deep space, far from everything. Inside, both feel exactly the same. You float, the apple floats. As long as your elevator is small and you don't watch for too long, there is no experiment that tells you which one you're in. Falling and floating in space are the same experience. How small is small enough? Here's the giveaway. If your elevator were as big as a stadium and you let go of two apples far apart, near Earth, they'd slowly drift toward each other because each one is falling toward the center of the Earth, and those directions aren't quite parallel. Out in deep space, they just hang there. Shrink the room, and that clue disappears. Einstein's rule is a rule about small rooms. Now flip it. Version 3, the elevator sits parked on Earth, and you feel your normal weight pressing your feet into the floor. Version 4, the elevator is in deep space, but a rocket underneath is speeding it up, faster and faster. That acceleration presses you into the floor with the exact same feeling. Again, in a small room, no experiment inside can tell the difference. Gravity and acceleration wear the same disguise. Einstein made that a law of nature and called it the equivalence principle. And that little law has a huge hidden prize. Shine a flashlight sideways through the accelerating space elevator. While the light crosses the room speeds upward. So from inside, the beam appears to bend down, like a slow motion waterfall of light. But wait, if acceleration bends light and gravity is indistinguishable from acceleration, then gravity must bend light too. Light has no mass at all. You couldn't put it on a scale, and gravity bends it anyway, which means gravity is doing something much sneakier than pulling on stuff. So here is Einstein's answer, the heart of general relativity. Gravity is not a force reaching out and grabbing you. Gravity is the shape of space and time. Every chunk of mass and energy bends the space and time around it, the way pulling a thread puckers a piece of cloth. And everything moving through that bent region simply follows the straightest path it can. We call that curved path following gravity. You may have seen the famous picture, a bowling ball sagging a trampoline, marbles curving around the dent. It's a decent start, and I'll show it to you, but I have to be honest. It cheats. It uses Earth's gravity pulling the ball down to explain gravity, which is circular, and it shows only space bending. The real secret, the part almost nobody tells you, is that for slow things, a dropped ball, the moon, the bending that matters most isn't space, it's time. Light is the one exception. It moves so fast that the bending of space counts just as much, which is exactly why starlight bends twice as far as old-fashioned gravity math predicts. Here's the real secret. Clocks closer to a heavy planet genuinely tick slower than clocks higher up. Your feet age a tiny bit slower than your head. That's not a metaphor. We've measured it with clocks on shelves 1 foot apart. So near the Earth, there's a kind of slope in time itself. Slower down low, faster up high. One quick word before the payoff. Physicists stopped treating space and time as two separate things. They glued them together into a single fabric and gave it one name, space-time. You are always traveling through it. And gravity is nothing more than the shape of that fabric. And here's the payoff. You are always moving through time. Even sitting perfectly still, you are traveling into tomorrow at a steady rate. Now, near the Earth, time runs unevenly, slower down low, faster up high. So the straightest path you can take through that uneven time doesn't stay level. It leans toward the slow side. That lean is what we've been calling falling. Nothing yanks the apple. No rope, no force, no invisible hand. The apple is coasting, dead straight through crooked time. Same with the moon. Nothing is holding the moon on a leash. The Earth bends the space time around itself, and the moon just coasts straight ahead forever to that bent region which loops its path into a circle. Orbiting is falling around something instead of into it. As the great physicist John Wheeler put it, matter tells space-time how to curve, and space-time tells matter how to move. That's general relativity in one sentence. Okay, slow clocks, bent light, crooked time. How do we know all this is actually true and not just a beautiful story? Because the universe has been grading Einstein's homework for over 100 years, and he keeps getting an A. Let me show you the 5 coolest check marks. Checkmark 1, Mercury. For decades, astronomers were bugged by the planet Mercury. Its oval orbit slowly swivels around the sun, like drawing with a spirograph, and Newton's old gravity math predicted the swivel slightly wrong. Just a smidge, but stubbornly wrong. Einstein redid the math with curved spacetime, and it came out exactly right, no fudging. He was so excited he had heart palpitations. Checkmark 2, bent starlight. If the sun curves spacetime, then starlight passing close to the sun should bend, making those stars appear slightly out of place. You can only check during a total eclipse when the sky is dark enough to see stars near the sun. In 1919, astronomers sailed to Africa and Brazil, photographed an eclipse, and there it was. The stars had shifted, right where Einstein said. It made headlines around the world, and Einstein woke up the most famous scientist alive. Checkmark 3 is in your pocket. GPS. Your phone finds you by listening to super precise clocks on satellites, but those clocks are doing both of Einstein's tricks at once. They're moving fast, so special relativity says they run a little slow, and they're high up where time is less bent by Earth, so general relativity says they run a little fast. The fast forward wins. The satellite clocks gain about 38 millionths of a second every day. Sounds like nothing? If engineers didn't correct for it, GPS would drift off by about 7 miles every single day. Every time your map app works, it's proving Einstein right. Checkmark 4, black holes. Einstein's math predicted places where so much mass crams into so little room that space-time bends beyond escape. Fall in, and not even light gets out. For a century, they were theory. Then in 2019, scientists linked radio telescopes across the whole planet into one Earth-sized camera and actually photographed one. A glowing golden ring around a perfect dark shadow, 55 million light years away. It looked almost exactly like the equation said it would. And checkmark 5, my favorite. If space-time can bend, it can also ripple. Einstein predicted that colliding black holes would shake space-time like a drum, sending out waves. He doubted we could ever detect them. The stretch is smaller than a single proton, millions of times smaller than an atom. But in 2015, a pair of instruments with lasers miles long felt space itself stretch and squeeze as the ripple from two black holes colliding over 1 billion years ago rolled through the Earth. Through you. We heard space-time ring. Before we finish, let me answer the 4 questions every kid asks me. Question 1, is time travel real? To the future? Yes. Genuinely, provably yes. Move very fast or hang out near something very heavy, and less time passes for you than for everyone else. Come back, and you've skipped ahead. Our record holder is a cosmonaut who spent so long orbiting fast that he's about a 50th of a second younger than he would have been. Tiny, but real. Time travel to the past? Almost every physicist thinks no. The past seems to be a one-way door. Question 2. Why can't anything beat light? Two reasons. First, pushing something with mass faster and faster takes more and more energy, and getting it to light speed would take more energy than exists. But the deeper reason is stranger, because now is different for different movers. A message traveling faster than light would, for someone, arrive before it was sent, effect before cause, and answer before the question. The universe's speed limit isn't really about speed, it's about protecting the order of cause and effect. Question 3. What's actually inside a black hole? Honest answer, nobody knows. Einstein's equations stop making sense at the very center. They start spitting out infinities, which is usually math's way of saying, I'm broken, send help. That's not embarrassing, that's exciting. It's a giant sign at the edge of the map that says, here be a discovery nobody has made yet. Question 4. Does any of this affect me, a kid, today? You've been affected this whole video. Your GPS works because of it. The sunshine on your face is E equals mc squared, live. Your feet are aging slower than your head right now, and every glance at the night sky is a view through curved space-time. Relativity isn't a faraway theory about rockets. It's the operating system of everything, including you. So let's count what Einstein asked us to give up. We gave up the master clock. Now is not the same for everyone. We gave up solid, dependable distance. Rulers shrink. We gave up gravity as a pull. It's the shape of space and time, and mostly the crookedness of time. In exchange, we got a universe far stranger and far more beautiful than anyone imagined, and one that we can check. That's the deal science offers. Believe nothing, test everything. Two honest notes before you go. First, everything I showed you is real, but simplified. The full theory is written in math you'll be ready for sooner than you think. Second, even Einstein's masterpiece isn't the end of the story. Deep inside black holes, and at the first instant of the universe, general relativity and the physics of tiny things stop agreeing with each other. Somebody has to fix that. Maybe somebody watching this. Tonight, if you can, go look at the stars. Starlight bending around galaxies on its way to your eyes. Satellites overhead running Einstein's corrections so your parents don't get lost. Your feet aging slower than your head. You live inside relativity. You always have. Now you're one of the people who knows it. Thanks for watching.